In our last video, we said that bounded sequences do not necessarily converge. But to end this section on a good note, this video we're going to talk about well, if our sequence is bounded and it possesses some other property, it will converge. And so what is the other property? And so we want to talk here about monotonic sequences. What are monotonic sequences? So we say a sequence a sub n is increasing if a sub n is less than a sub n plus 1 for all n. So each successive term is bigger than the previous term. A sub n is decreasing if a sub n is bigger than a sub n plus 1 for all n. Each successive term is smaller than the previous term. And so what's monotonic sequences? So a sub n is monotonic if either increasing or decreasing. So let's just draw a couple pictures here. Axes going on here. So let me draw a monotonically increasing sequence. Dot, dot, dot. So sometimes the increase might be big, sometimes the increase must be small, but each term must be bigger than the previous term. The blue dots are a monotonically increasing term. Let's have a monotonically increasing sequence. How about monotonically decreasing sequence? So each term must be smaller than the previous term. If you have any back and forth, like if we have this, okay, it looks like it's increasing, now it goes back down. This purple sequence I'm just drawing right here, this is not a monotonic sequence. So when we say monotonic, means always increasing or always decreasing. The purple sequence does not work. Okay, so our big finale here, bounded monotonic sequences converge. A sub n is an increasing sequence, and m here is an upper bound. So an increasing sequence and it's upper bounded, then a sub n converges and the limit as n goes to infinity, a sub n is less than or equal to that upper bound. And also a sub n is a decreasing sequence and p is a lower bound on the sequence. Again, our sequence converges and the limit is greater than or equal to our lower bound. So to put all of this together, if your sequence is bounded and is monotonic, it must converge. Let's just kind of draw a picture. Let's draw out a picture for that first case here. So we have a sequence. So suppose that we have our sequence is increasing like that here. Okay, so we say that we are also given, as part of the assumption, a sub n is increasing and there's an upper bound m. Okay, there's m right there. Also note that increasing sequences, monotonic sequences are always bounded in the other direction. Here's a lower bound on our sequence. And so the sequence can't go off to infinity. And I mean, there's a little bit of proof that we're glossing over here, but you can prove that either m is the limit or it converges something a little bit less than m. So increasing sequence that's bounded above, bounded overall means bounded above. This is going to converge. In the picture, it looks just exactly the same to do the other part here, that if a sub n is decreasing and it's bounded below, your sequence also converges. Okay, so to finish off this video set here, suppose that we have a sub n is equal to square root of n plus 1 minus square root n here. We want to show that this, we want to show that this sequence converges. How do we do that? So we observe that a sub n is decreasing. How can we show that a sub n is decreasing? Well, derivatives. So we can think about the function f of x is square root of x plus 1 minus square root x. And f prime of x is 1 over 2 square root x plus 1 minus 1 over 2 square root x. Sorry, that should be x plus 1 there. And you can convince yourself that this is positive. Why? Oh, sorry, not positive. It's negative. We want to show that this is decreasing because of the two terms here, they look very much the same. Here's square root x plus 1. Here's a square root x. X plus 1 is bigger than x. The denominator here is bigger than the denominator here. So this fraction is smaller than this fraction. So this is negative. So a sub n is a decreasing function. And also we observe that a sub n is always always strictly positive. Square root n plus 1 is always bigger than square root n. So this tells us that 0 is a lower bound. So by this theorem right here, we conclude that this converges. And maybe just one last example that just occurred to me. In the previous video, we saw a sub n was equal to 3 minus 1 over n. We said that this is an increasing sequence. It's not too hard to see that this is an increasing sequence, and it's bounded above by 3. So each term is bigger than the last because we're subtracting off successively smaller things. And you can see that, yes, this is going to converge to 3. Okay, that is a wrap on section 10.1.